So as we begin to talk about management practices that farmers can use to reduce nutrient losses from their farms, let's take a step sideways and ask this question. How can we assess the risk of nutrient loss from a farm? If we can't measure this, we can't know if we're heading in the right direction, and that's going to be the focus of today's talk. One really useful tool that is being used on dairy and other livestock farms all across the US and around the world is called the whole farm nutrient balance. So what is a whole farm nutrient balance? It's an accounting tool in which we quantify all of the nutrients coming onto the farm and all of the nutrients leaving the farm in some managed product. So, for instance, if we buy animals, those animals contain nitrogen in their bodies, right, and phosphorus, so we're bringing nutrients onto the farm. Feed and fertilizer are always the dominant sources of nutrient inputs onto dairy and livestock farms. Legumes is one you might not think of, but if we basically are drawing a box around the farm and saying, how are nutrients coming onto this farm, then we do need to account for the nitrogen that is fixed by legumes. Also, if we're pumping on any irrigation water, in most situations in the east, this is not going to be an issue because there is negligible nitrogen or phosphorus in the water from the river that we might irrigate with, for instance. But there are some situations, especially out west, where you might be irrigating with gray water that may contain nutrients. So we need to quantify all of those nutrients onto the farm. Then let's look at the nutrients leaving the farm. Milk, eggs, meat, if we're selling any crops, if we're selling any compost. And if you think about it from an accounting perspective, inputs minus outputs, let's think about this imbalance, because if we're bringing more nutrients onto the farm than are leaving in managed products, those are the nutrients that have potential to leave in an unmanaged way to pollute the environment. Let's dig a little deeper and I'll give you some examples. I think this will become more clear. And so on this slide we have a beef feedlot example, a small dairy farm example, and a farrow to finish hog farm example. And in each case, what we're looking at in terms of inputs and outputs are similar to what you saw on the previous slide. So the inputs onto the feedlot, for the most part, it's going to be grain, maybe some hay, and also the calves that are brought onto the feedlot each year. The managed outputs are those calves all grown up. It's when animals leave the farm, that is where we're capturing those nutrients that came onto the farm. We're literally feeding the grain to the cows and capturing that in their bodies, and we account for that, and that's the managed output. The imbalance on a feedlot in this situation for nitrogen is about 650 tons per year. Much more useful to express this in a ratio. So inputs over outputs. For nitrogen on this example, beef feedlot, it'd be about 2.5 to 1. For phosphorus, about 2 to 1. And honestly, those are pretty good. That's a pretty decent whole farm nutrient balance, whole farm nutrient ratio, because it's a biological system. We can't hardly do any better than capturing 50% of the nutrients that we feed to an animal in meat, milk, or eggs. So 2 or 2.5 to 1 is pretty good, pretty efficient. But it does still leave some nitrogen and some phosphorus that may accumulate and run off or leach, contaminating the environment. On the dairy farm, again, your inputs are going to be feed, probably some fertilizer. Maybe we're growing some legumes to have some alfalfa silage to feed. We've got to account for that in terms of nitrogen. Managed outputs, almost entirely going to be milk. But also, if we're selling any animals for dairy, or if we're selling any animals, so cull cows, veal calves, maybe. So the managed outputs are going to be dominated by milk, but also the animals themselves. So every dairy farm has a certain number of cull cows every year that are leaving. If they're selling any cows for dairy, so selling heifers in a purebred sale, for instance, we have to account for that because that's where the nutrients that we brought onto the farm are being deposited, in that cow's tissue. Also, think about male calves. Generally, those are shipped early on to become veal, so we've got to account for that. Again, if we're selling any manure, if we're selling any crops to the neighbor down the road. Any nutrients that cross the farm boundary. And the hog farrow to finish, again, fairly simple. It's going to be mostly feed coming in, and mostly hogs going out, unless, again, they're selling some manure, growing any crops. And so with this ratio of nutrient inputs to nutrient outputs, we get a sense of the risk of nutrient loss from the farm. It's an accounting measure. So again, you're drawing a boundary around the farm, you're putting a box around the farm, and you're just quantifying everything that comes across that boundary, and that will give you your whole farm nutrient balance. So the whole farm nutrient balance just gives us a sense of the mass of nutrients that we're bringing onto the farm and exporting from the farm, and giving us a sense then of the mass of nutrients that can't be accounted for in product. And so it's those nutrients we need to worry about and try to control and keep from running off or leaching. So that's whole farm nutrient balance. It's what crosses the boundaries. Now, what happens inside of those boundaries is what drives the efficiency with which we're using those nutrients. And so how we manage the nutrients does matter. And within the farm, we've got feed coming in, being fed to the animals, those animal products being exported. The animals are excreting manure. That manure may be land applied. If it's a beef feedlot, maybe they are exporting manure and selling it. Then the manure is land applied to crops. There's fertilizer entering the cycle there. Those crops are fed to cows, which we export product, and they excrete manure, which we land apply to grow the crops to feed the cows. All right, so this nutrient cycling within the farm boundary is tremendously important. It gives us a sense of where we can intervene to make our nutrient use more efficient. So two concepts here. Whole farm nutrient balance is literally the nutrients that cross the farm boundary. It's just an accounting exercise. But where we want to find ways to intervene and improve efficiency, we need to look at the nutrient cycling within the farm. So the opportunities for intervention are in your cropping strategies, in the diets that you're feeding the animals, in marketing. So if we have more of an imbalance of nutrients than what we really desire, well, can we sell manure? Can we compost it and make that into a desirable end product to export it off the farm? Are there ways we can make our animals more efficient? Anything we can do to improve the managed product, increase the managed product for that same amount of nutrient input, that is going to reduce our nutrient imbalance and reduce our environmental risk. In the rest of the talk, I'm going to focus in on diet as a strategy to achieve a more desirable whole farm nutrient balance. So let's talk about one of the key ways to address a nutrient imbalance, and that is what we'll call dietary nutrient management. Because what goes in the front end of the animal must come out the back end of the animal. Although both nitrogen and phosphorus in manure can cause environmental problems, in today's talk I'm going to focus largely on phosphorus, and that's because remember that in manure, phosphorus is in imbalance with nitrogen relative to crop needs. So when we apply manure to meet the nitrogen needs of a crop, we are always over-applying phosphorus. Over time, phosphorus can accumulate and run off and contaminate surface water systems. So it's that basic imbalance in manure that is a really important point. So as you read, the challenge with nitrogen and phosphorus in terms of water quality is largely associated with eutrophication, or an overgrowth of algae. This particular slide shows what happens when you add too much phosphorus to freshwater systems, and on the one side where they've added the phosphorus, you can see the algae bloom, the overgrowth of algae. And when that algae dies, it sucks the oxygen right out of the water, and really nothing can survive in that area. We call that a dead zone. Nitrogen causes the same impact in saltwater systems. And I'm not going to talk about it today, but of course remember that nitrates can also leach into groundwater and have human health impacts. So back to whole farm nutrient balance. As I said, feed ingredients are the number one source of nutrient imports on most dairy and livestock farms. Usually they will account for 2/3 or 70% of the nutrients brought onto the farm. And so even though nutrition is tremendously important to the health and productivity of the herd or the flock, if there is a nutrient imbalance, then often we need to consider nutrition as the source of the problem. And the good thing about this particular problem problem is there's a solution. The solution is to more precisely define and meet the nutrient requirements of the animals. So what am I talking about? What I'm talking about is less overfeeding for insurance. This idea that if a little is good, more must be better is one we need to let go of. And in so doing, we can reduce nutrient excretion, reduce the nutrient content of the manure, minimizing the nutrient imbalance and reducing the potential contamination of ground and surface water. So here's where we're going today. I've got about a half a dozen quick questions, and you can stop and think about these now, and just make sure that by the end of this presentation that you're able to answer all of them. And so the first question is, why do livestock require phosphorus? Livestock do require phosphorus, all species do. It's true that there is more phosphorus in livestock manure than crops need, at least relative to the nitrogen content of the manure, but that doesn't avoid the fact that all species require phosphorus. They require it to build bones, they require it for important buffer systems throughout the body, and also phosphorus is a critical component of energy metabolism systems in animals. And they get the phosphorus that they need from two key sources in the diet. The first is just as part of the basal ingredients. Grains and forages, byproduct feeds, all of these contain a fair amount of phosphorus. We also supplement phosphorus to livestock and dairy diets by way of mineral supplements, so dicalcium phosphate, monocalcium phosphate, monosodium phosphate. There are a variety of mineral sources of phosphorus that are used to supplement any needs beyond what is provided from the diet. The problem comes when we feed too much phosphorus. When we feed more phosphorus than the animal needs, that extra phosphorus comes right out the other end in manure. The data shown on this slide is the very first research study I did when I came to Virginia Tech. I had 13 early lactation dairy cows. I think I had 13 students working for me to collect the manure samples from these cows, and they collected every bit of urine and feces that those cows excreted while I fed them 3 different levels of dietary phosphorus. 0.34, 0.52, which was the average that we were seeing in the field, and 0.67% phosphorus, which we had some herds that were feeding that much phosphorus. And as we plotted phosphorus excretion in grams per day compared to dietary phosphorus, what we found was that every extra gram of phosphorus fed beyond the requirement came right out the other end in manure. That 0.34% phosphorus is just about what we now know is the requirement for dairy cows. It varies just a little bit, but it's going to be in the mid-3s. And so as we increase that dietary phosphorus above that level, every extra bit came out the other end, and it did those cows no good at all. Surveys since then are showing us that in all species we are often feeding more phosphorus than what the animal requires. Why is this? So as we talk to farmers about this, we're hearing several different reasons, but increasingly the second bullet is the one that dominates. I think over the last decade or so we've made a lot of progress in research, and then bringing that research to farmers, reassuring them that our published requirements for phosphorus are in fact accurate, that it really is true that dairy cows and beef cattle don't require supplemental phosphorus in their diets. I think the feed companies have come a long way in realizing that that extra phosphorus is not needed. But one real problem, I think, is undetected variation in feed phosphorus and some problem feeds, and I'm going to talk about those here in just a minute. For a long time, what we were hearing was a belief that dietary phosphorus was linked to reproductive performance. I think we have put that old myth to bed, but just in case, let me talk that through with you. So some researchers in Wisconsin decided to tackle this question head on, and what they did is they pulled together the results from 13 experiments done in the 90s with 785 mature cows. So they did a meta-analysis of this, and they just asked the question, is there any evidence with modern dairy cows of any link between dietary phosphorus and reproductive performance? The answer was a resounding no. There was no difference between the low and the high phosphorus diets in days to first estrus, days to first AI, no difference in days open between the cows across these studies who were fed low phosphorus or high phosphorus. There was no difference in services per conception. There was no differences in conception rate, again, between the cows in all of these studies who were fed low phosphorus compared to the cows in the same studies fed high phosphorus. So I think this meta-analysis really helped to reassure the industry, and so I don't hear this anymore. In case you hear it, the answer is no. There's no relationship between dietary phosphorus and reproductive performance. Let me briefly touch on beef cattle because the same concept holds true, that overfeeding phosphorus directly increases the phosphorus content of manure. Then Galen Erickson out of Nebraska did the same kind of research with beef cattle that others did with dairy cattle, and basically found no effect of dietary phosphorus on any of the important growth or efficiency characteristics. Also, no effect of dietary phosphorus on bone strength and marbling and meat tenderness. And if you look at the dietary phosphorus, the range that he tested, all the way down to 0.14% phosphorus. So requirement for beef cattle is a lot lower than was conventional wisdom for many years. Let's also talk briefly about monogastrics, pigs and chickens and turkeys, because there are several dietary strategies that can make a real difference in the nutrient excretion by these species. These strategies include reduced overfeeding, just as in beef and dairy cattle, and phase feeding is a strategy that has been used very effectively by the swine and poultry industries to reduce overfeeding of phosphorus. And this is simply dividing the herd or the flock into groups of animals with homogeneous nutrient requirements. Piglets, the first week or two of life, have much higher and different nitrogen and phosphorus requirements than hogs later in the growth cycle. Split sex feeding, the same concept. Males and females often have very different nutrient requirements, so house them differently, feed them differently, fine-tune those diets specifically for the nutrient needs of the animals that you're feeding. The last two bullets, low phytic acid grains and phytase, deserve special mention because they have become really important in the last decade in terms of reducing the phosphorus content of hog manure as well as poultry litter. To understand what phytase does, you first have to know what phytic acid is. Phytic acid is an organic compound that contains a great deal of phosphorus, and the vast majority of phosphorus in cereal grains like corn and wheat and oats is bound to phytic acid. This is not available to monogastrics. For ruminants, it is available because rumen bacteria are able to break down phytic acid, but in monogastrics, the phosphorus attached to phytic acid is not available. Phytase catalyzes the breakdown of this compound, releasing the phosphorus and making it available to the animal. With the use of this enzyme phytase, or with grains that have been bred to have a low phytic acid content, the phosphorus in the grain is more available to the animal. We can reduce the phosphorus content of the manure. 3 points of clarification. The first is to be sure to distinguish between phytase, the enzyme, and phytic acid, the compound that is broken down by the enzyme. A second point, you'll see phytic acid also referred to as phytate, P-H-Y-T-A-T-E. Those are synonyms. Phytase is the enzyme, phytic acid or phytate is the compound. The third point of clarification is why exactly we're able to reduce phosphorus excretion with the addition of phytase. Typical practice is to add mineral phosphorus to hog and poultry diets because the phytic acid phosphorus is not available. When we add phytase, we don't have to add as much mineral phosphorus because now we can count on the phosphorus in the cereal grains as a source of phosphorus for the animal. The development of this technology, the exogenous phytase enzymes, has had a powerful impact on the phosphorus content of hog manure. We can be proud as Hokies because most of the work developing and then testing phytases was done right here at Virginia Tech. E.T. Cornegay was a renowned animal science professor, and then his work was followed up on by Alan Harper, who just recently retired. This table is some of Alan Harper's data, and what he's showing here is the dramatic impact on phosphorus excretion that can be obtained with the addition of phytase. So he's got a control diet containing 0.5% of phosphorus. Then the low phosphorus diets, he added phytase. And so in the second line, you can see he was able to reduce the phosphorus intake by the pigs. And the third line, reducing the phosphorus excretion, especially with that higher level of phytase, by as much as 27%. So this technology has been widely adopted in the hog industry and is a real success story. I want to change gears for just a minute and tell you that there are reasons beyond just the environmental that we really need to pay attention to the phosphorus feeding practices in our industry. And that is that phosphate is a limited resource. Phosphate is mined, of course, and it turns out that most of the phosphate mines are in areas of the world that frankly are a little unstable and are not always friendly to the United States. So phosphorus is a limited resource. Most scientists predict that peak phosphate production will be in about 20 or 30 years, and that following that point, we're looking at a fairly quick drop-off in the supply of rock phosphate. And so that means that paying attention to dietary phosphorus is of economic importance as well as environmental importance. I'm going to shift gears again and move away from phosphorus and talk about nitrogen and some of the dietary strategies that we can use to reduce nitrogen excretion by all of our species. There's a great deal of variation between the species in terms of how efficiently they utilize dietary nitrogen. There's also a great deal of variation within a species in terms of how they utilize it. Where there is variation, there is always opportunity for improvement. Just as with phosphorus, there is a degree of overfeeding of nitrogen or overfeeding of phosphorus in many of our species. Dr. Hannigan upstairs has done work for many years trying to identify optimal dietary protein, the point at which we are maximizing milk yield and minimizing nitrogen excretion. And that sweet spot is 15 to 16% protein, whereas common practice in the industry is often about 17 or 18% dietary protein. So there's opportunity to reduce nitrogen excretion through reduced overfeeding. So how do we achieve that? How do we obtain maximum milk yield with minimal dietary protein? To answer that question, I'm going to just review a little bit from ALS nutrition, or if you haven't had that course yet, I'll tell you just as much as you need to know about protein nutrition to help understand how we can change diets. So proteins, of course, are molecules. They're made up of amino acids. Proteins supply most of the nitrogen to the animal. We can convert from the crude protein content of the diet to the nitrogen content of the diet, or vice versa. Nitrogen times 6.25 equals crude protein. The quality of protein in feeds varies. It's primarily a function of the digestibility of that protein and its amino acid profile. AA will be the abbreviation for amino acids. Animal products typically have a better amino acid profile in terms of what the animals need than do plant proteins. An important concept is this concept of the first limiting amino acid. So let's talk about that a little more deeply. Proteins are a combination of amino acids, and they will contain varying numbers of those specific amino acids. So a protein might contain 5 times more tryptophan than methionine, let's say. The concept of the first limiting amino acid is that the muscle stops growing, protein formation stops the first time they run out of an amino acid. So there might be plenty of tryptophan left, but when they run out of methionine, protein synthesis just flat stops. The important part of this concept is that the extra of tryptophan or whatever extra amino acids are in the diet are going to be excreted. So when they run out of the first amino acid, synthesis stops, all that extra nitrogen is excreted. So there's 2 ways to solve this problem. The first and inefficient way is just jack up the protein content, just feed way more protein than the animal needs so that they'll never run out of any amino acids. Now, obviously, this is not the approach we want to take, because then we are going to be just way overfeeding nitrogen, all because of one amino acid. The better way to solve this problem is to add just tiny little bits of the specific amino acids that we know they're going to run out of first. So we add crystalline amino acids to more precisely meet the needs of the animal. So we can add just that little bit of methionine, just that little bit of lysine that is needed in order to match up with all the other amino acids in our basal diet. So we can feed less total protein and add just these little bits of crystalline amino acids and reduce nitrogen excretion. So the concept of crystalline amino acids is well established and well adopted in the hog and poultry industries. But as usual, ruminants are just a little bit more complicated. Just as with monogastrics, what goes in the front end must come out the back end. In the case of cows, it's going to be milk, urine, and feces. What makes cows more complicated is what happens in between, and that is the impact of the rumen bacteria. Now, the rumen bacteria are what make cows great. They are what allows a cow to utilize high fiber feeds that humans and other monogastrics cannot utilize, and they turn those feeds into great quality protein. You probably know this from your nutrition classes, but just in case, the rumen bacteria are breaking down the starch, the fiber, the protein in the feed, and it's when the bacteria die, they themselves become the source of the protein. I mean, the bacteria die, they flow down to the small intestine, their bodies are digested, and it's the amino acids from the bacteria's bodies that actually provide most of the nitrogen that a ruminant needs. And this protein is of really pretty high quality. It matches the needs of the cows really pretty well. But as much as we appreciate what the rumen bacteria do, they also make things complicated. With pigs and chickens, we can be pretty confident that if we add a specific amino acid to the diet, a little more methionine, that amino acid is going to show up in the small intestine, going to be absorbed. But with a cow, with a ruminant, whatever you feed, the bacteria are going to rip it apart and create their own bacterial protein with it. So we can't count on adding specific amino acids to the diet the way we can with monogastrics. But we're scientists, so we have to try, and what we do with ruminant diets is we use a concept called degraded and undegraded intake protein. You'll see this abbreviated UIP for undegraded intake protein. We try to estimate how much protein in a specific feed might escape those rumen bacteria and arrive at the small intestine intact. We try to estimate what that protein that does escape the rumen bacteria might look like, what its amino acid profile is, and then we take those crystalline amino acids and we wrap them in something. We try to protect them from the rumen bacteria, and we add them to the diet, again just trying to make sure the absolutely perfect balance of amino acids hits the small intestine. And if we can do that, then we can keep dietary protein low. We can find that optimal level of dietary protein. The lowest total protein that will maximize milk yield and growth is always going to be the one that yields the most perfect amino acid balance when it hits the small intestine. And with that, I think I'm going to wrap up this lecture. There are a few take-home messages. The first is that manure composition varies with diet, that what goes in the front end of the animal absolutely influences what comes out the other end of the animal. So to reduce manure phosphorus content, stop overfeeding phosphorus. And in monogastrics, let's make sure that we are utilizing exogenous phytase so that we can meet the needs of the pigs or the broilers or the turkeys or the layers with minimal dietary phosphorus. When it comes to nitrogen, it's a little bit more tricky. With our monogastrics, we can look at crystalline amino acids, and with our ruminants, we're also getting to the point that we are getting pretty good at figuring out how we can protect amino acids from the bacteria and how we can add just the right amount of them to complement bacterial protein production. The ultimate goal with these dietary strategies is that we buy and feed only the nutrients that the animal really, really needs. And if we can do that optimally, we will increase their efficiency, we will reduce that nutrient imbalance, that whole farm nutrient imbalance.